In this video, you're going to watch a live class of me demonstrating how to solve logarithms and how to sketch logarithms. Then, at the very end, we'll go through some of the key questions. See you in there. So this class in particular is going to cover about solving logarithms and sketching logarithms. So I guess the first thing we'll have a look at is just fundamentally what is a logarithm. Well, logarithms are all about essentially rewriting an equivalent exponential equation into an equivalent logarithm equation. So if you have some exponential y equals a to the power of x, then all you really have to do is flip the order of those terms to convert it into an equivalent logarithm form. Fair enough so far?
Yeah.
Yep. So for a quick example, this one is a pretty simple one. If you have 6 equals 4 to the power of x, then all you would do is swap the bases. So the base of the exponential is always the same as the base of the logarithm, and whatever it equals goes inside the brackets. Whatever the exponent is becomes the subject of your equation. That relationship allows you to solve logarithmic equations, so you can always convert back and forth between logarithm and exponential to solve for whatever the unknown is that you're solving. It works for solving exponentials, it works for solving logarithms. Very quickly, the inverse of a logarithm is always its equivalent exponential. This is simply just a consequence of how you would solve for inverses in general. So you'd start by just swapping the x and y, and then rearranging for y. And if you do that for the exponential, you go from having y equals a to the x, and that becomes x equals a to the y. The only way to then rearrange for y is if you convert it to a logarithm. So you get back to having y equals log ax. You can see that these are inverse pairs of each other. Is that fair enough?
Yeah.
Cool. Okay, some of the typical logarithms that could come up. The most typical one by far would be the natural logarithm. That will look like log e of x most of the time, or sometimes you'll see ln of x, natural log of x, and that's what you'll see on your CAS. So if you see, zooming in, that term there, e to the x, how it's got that grayed out ln, that is your natural logarithm. The other possible logarithm that would come up, at least that has a different terminology, would be like the common logarithm, having a base of 10. Despite its name, it is less common that will come up as opposed to the natural logarithm. It gets its name from our number system. So our number system is a base 10 system. You have 10 digits. That's why it's the so-called common logarithm. It shares the same base as our number system. So that might be written as log 10 of x, or with a capital L instead, and there will be no base to speak of. Clear enough?
Yeah.
Nice. Okay, an overview of the logarithm laws. So just like you have index laws for the exponentials, you also have logarithm laws for the logarithms. Technically, those are pretty much the same thing. It's just how it appears differently in a different format because you're using logarithms. So some things worth pointing out to begin with. First thing is that your log laws pretty much will only ever apply if your logarithms have the same base. So you'll notice very quickly that if you look at all the highlighted things here, all of those logarithms have the same base. The next thing is more of a guideline. Try not to use log laws if you have coefficients out the front of your logarithm. So you can technically get around it by doing some factorizing approaches or by condensing down your logarithms, but just make life easier on yourself. And if you have a coefficient, you might want to consider bringing it into the power of your brackets, which we'll see how to do with the power law, or otherwise get rid of that coefficient in some way, shape, or form. But okay, the three main laws that we cover are the product law, quotient law, and power law. Basically put, if you have two logarithms with the same base added together, then the resulting logarithm, or you could combine that down into a logarithm that is the product of those two terms. So you got the m from here, the n from here, and you just multiply the two. This left-hand side is the exact same thing as that right-hand side. So this works both ways. If you have the right, you can replace it with the left, If you have the left, you can split it up into the right-hand side. Clear enough?
Yeah.
Cool. Quotient law, very similar, except this time we have a subtraction and a division. So the nature of subtraction means that you really have to pay attention to what becomes a numerator and what becomes the denominator. So the first term becomes your numerator, the second term becomes your denominator. But otherwise, it's just a plug and play there. And then lastly, the one that gets used a lot is the power law. So if you have something raised to a power, then you can bring that power out the front of that bracket. Now, I'll mention a nuance on that. If you, for instance, if I go to the handwritten bit, if you had, let's say, natural log of x squared y, you can't bring that power out the front. And the reason why is because the whole bracket hasn't been raised to the same power. So under these circumstances, you can't really use the power law. But if you instead had natural log of x squared y squared, then you could take this 2 out the front because then it's a common power. You can just use your index laws to convert that to xy squared, and now the whole thing hasn't raised to a power. Clear enough the nuance there?
Yeah.
Nice. Okay, you might see these called logarithm laws in the book. I've called them logarithm identities because they're more so just inherent results for logarithms rather than just a property of how logarithms can be used algebraically. Fundamentally, all of them can be proven by converting your logarithm to an equivalent exponential form and then solving that exponential. So if you're ever confused on which of the 5 identities is applicable to what you have, or if you're ever confused on exactly what the value should be, just convert to an exponential and then you'll be able to prove it. And we'll see a few examples of how that works. So first things first, if the base and bracket, so here's your base, here's your bracket, if those are identical, then the logarithm will always equal 1. So to prove that, let's pretend that we don't know what the left-hand side is equal to, and we're just going to call it y. We're not sure what it is. If you convert this to exponential, you get a to the y equals a. And very quickly, you'll see that this will only ever be true if y equals 1. So if y equals 1, then we can say that log a of a must therefore equal 1. Cool?
Yeah.
Nice. Okay, that proof will hold for literally everything that we have a look at. So identity 2. If your bracket is 1, then it doesn't really matter what your base is, the logarithm will always equal 0. So again, if we convert that to an exponential form, the only way that this left-hand side will equal 1 is if your power was 0. These are pretty common ones. Having a bracket of 1 and having a bracket and base the same, that comes up a lot. This here is more so for helping you understand whether or not your logarithm has a solution, or helping you figure out like maximal domains of logarithms. Basically put, if your brackets are negative, the logarithm has a non-real solution. This really only matters if you're doing spec math to specify non-real versus does not exist or undefined. But it's worth at least highlighting the nuance there, because technically there is a complex number solution to this. It's just not math methods related. So again, the reason why it's non-real is because if you do make it equal something, you've got a to the y equals negative b. Now that poses an issue because if you have a big y value, then you're just going to get a bigger left-hand side. And if you have a negative y value, it just means you have 1 over a certain value, which means you're just asymptotically approaching 0, but never actually flipping to negative. And yeah, I've just written a few things here as to basically if you did try to rearrange in some certain way, you would get the square root of a negative number, which, as far as we're concerned, is a non-real result. Okay, the slight nuance here, if you have a bracket of 0, then it's undefined rather than non-real. Undefined because a to the power of y as an exponential will only ever asymptotically approach 0, but never actually equal 0. And you can see that just from the basic, the generic exponential graph. And then I used to think this one was very, very niche. Now it's only pretty niche. It comes up more times than I thought it used to. Um, it looks like a bit complicated of one. It's the idea is that if your exponential is raised to a logarithm with the same base as your exponential, then whatever's in the brackets of that logarithm will always be the result of that left-hand side. This one's a little bit different of a proof. You still convert to exponential form, but you use the fact that we've already defined log a of x as y, and then you just replace this y at the top here with log ax, and suddenly you have a to the log ax is equal to x. It's come in handy so many individual times, but they're in pretty niche circumstances on the more complicated questions. Is this one clear enough?
Yeah.
Nice. Okay, this one is, I don't really know what you would call this, if it's an identity or a law. Either way, it's just, the idea is that you're trying to convert the base of your logarithm. The reason why you might do this is if the unknown that you're trying to solve for is trapped inside the base of your logarithm. So if we just take a quick look at the very end result here, if we're trying to, for example, solve for a is currently trapped in the base. But if you convert it to this right-hand side, you release it from the base and you then put it in the bracket. So that gets it one step closer to being solved. And we've already seen how you can solve things inside of a bracket. You can see here if you have log ax and you want to solve for x, you convert to exponential. So it's helpful for solving those kinds of questions. You first get it from the base into the bracket and then convert to get back out of the bracket of the logarithm. The other use case for converting the base of a logarithm is if you're trying to write your answer to a particular form. So you might have one answer, but it's saying, hey, write it in the form of log bx, whatever that might look like. Under those circumstances, you could convert your base and then achieve whatever specific form it's asking for. Clear enough on the use cases?
Yeah.
Okay. So there's the result at the end, but if you don't want to memorize that, then one thing you can always imagine is this three-step process instead. So just like everything else we've looked at, you would start by converting your logarithm to an equivalent exponential. What you would then do is choose whatever base you want your logarithm to be and apply that to both sides of your equation. So if b is your new desired base, then you would put a log b around both sides of this equation. So log b around this, log b around this. And then from there, you just rearrange for y, because y is that initial expression that we're trying to rewrite, which means using the power law to bring the y from here out to here, and then dividing both sides by this logarithm. So a tip on how to use this for solving, what you would typically do is choose your base to be the same as this bracket, or I guess maybe this bracket. Basically choosing the base to be the same as one of your brackets. And the reason why is because you would cancel that out. So we've seen earlier, identity 1, if you have same base and bracket, that is equal to 1. And so what that does is that it cancels out one of your logarithms in this fraction. You only have one logarithm instead of two. So that's just a tip at the end. Clear enough on how we got to this final result down here?
Yeah.
What do you think's easier, memorizing this or thinking about how it came to be?
I think for me, I like thinking about how, like, the steps. I think it's a bit easier to remember.
Yeah, I think so too. That's why I thought it might be nice to write it out. So yeah, that's there for you, of course, in the classroom to revise. Okay, examples. What did I say here? I do have work solutions to a particular chapter. Yeah, okay. This is because solving logarithms is basically akin to using algebra to solve things. So the best way to sort of understand how to do it is just do a bunch of examples. So that's the end of solving for logarithms. Got a whole summary there of all the different techniques that you can use, and that's fundamentally it. Anything I should clarify before moving on to the next topic?
With the complex numbers, do they come often in spesh, like with the in the logarithms form of logarithm?
Specifically logarithms?
Yeah.
Possibly. I'd imagine so, because Spesh does look at complex numbers pretty early on, and so
Yeah.
I don't see why I would shy away from doing it logarithm-wise. Yeah.
Yeah, because I've never come across a question with logarithms in spesh yet,
Yeah, okay.
like with
Uh,
complex logarithms.
sure. We could even take a quick break and have a look at the Spesh textbook and see if we can find something logarithm, complex number logarithm related. Let's see. Okay, textbook, Spesh, Cambridge, 34. Let's see if we can find some logarithms. Or maybe even just the complex numbers. Complex numbers.
I don't think there's any in the complex number
Yep.
chapter.
Okay. Logarithm. Oh, there's two results for logarithms. Interesting. Wow. Okay. So it only really appears in integrals and calculus. Yeah, just integrals. Okay. I guess it might not be a special thing then. But complex numbers certainly are a special thing. So
Yeah.
I guess I don't really want to look at it. Anyway, if it does look at it, then you'll at least see a bit of an explanation as to how you might solve that, or at least why it becomes complex. Yeah, interesting. I wonder why they avoid it. Or just it just doesn't even flat out show up like at all. For they just call it logs then? Oh, log e shows up a lot. Okay, that shows up too many times. Hmm. Okay, that's a bit more. Yeah, I wouldn't be surprised if you do see something complex number related then. Yeah, I didn't realize that the word logarithm would be so much less used than just saying log e. Interesting. Anyway, clear enough on how exponentials, logarithms are related to complex numbers?
Yeah.
Yeah. In fact, there is an identity. Oh, this will test me from engineering. I think there's a thing where it's like y equals e to the I theta, and that's like a way to do polar form, having e to the I something. Oh, what's
Yeah.
that related? And then obviously you could convert that to an equivalent logarithm, and that would therefore have logarithms as complex. Oh, that's testing me though. That's been a while since I've looked at that. But anyway, so that's that. Cool. As far as sketching logarithm goes, well, just like any other type of function, it also has a general form, and all of the terms in that general form work pretty much how you expect. The h is a horizontal translation, the c is a vertical translation, d and a are dilation factors, and you're not seeing them, but reflection terms work the exact same way as you think they do. Only thing that might be a little bit different to understand is that logarithms also have an additional term, which is the base, and that's also going to impact its shape, or at least the steepness of its shape. If we consider a basic logarithm that has a base greater than 1, so for example log 2 of x, you basically got a situation where you have this. You have a vertical asymptote at the origin, and you have a graph that is going from left to right, effectively, and ascending in that direction. So if you're ever confused on what the graph of a logarithm might look like, it might be worth first sketching an exponential equation and then just flipping that in the line y equals x. That's one way of remembering the shape. So depending on which one you like better, you can always find, or at least which one you memorize better, you can always flip that to figure out the other one. So logarithms will typically have a restricted domain because of this fact, right? Because we're asymptotically approaching x equals 0. And so basically the asymptote will always be whatever your horizontal translation is. As your base gets larger, what we're effectively doing is dilating along the x, or you could say from the y. And so if you compare log 2x to log 10 of x, Well, you see that the rate at which it shoots to the right-hand side is significantly condensed closer to the x-axis. It's getting further along the x. And you see a sort of opposite effect over here. So basically just tells you how steep the curve is. This one has a very sharp transition. Blue has a very gradual transition. The other thing worth considering is kind of like exponentials. If you have a base between 0 and 1, you have what is effectively a reflection. And so, again, trying to figure out what that will look like, you might want to then just consider the original exponential and then just flip that instead. But fundamentally, when you have a base between 0 and 1, you're reflecting in the x. You can see the x is acting like a mirror. So instead of going up and left, up and right rather, it goes down and right. Okay?
Yeah.
Nice. This time, as your base gets smaller, you see a dilation along the x. So instead of getting larger bases, you're now getting smaller bases to achieve the same effect. And that's because you're getting closer and closer to 0, as opposed to getting further and further away from 0. Proper dilation factors are the a and d terms here. A is a dilation factor along the y, or from the x. And so sure enough, if you have a bigger number out the front, it's going to rise faster since you're multiplying the y value of that function by a bigger number. So what would this, whatever this is, this will be 3 times larger over here. Oh, not 3 times, sorry. It'd be the difference between this and that. So 9 times larger, I suppose. And then the d value, again, this is just another dilation factor. This stuff only really matters if you're trying to sketch the same or 2 logarithms on the same axes. But it's worth at least understanding because you would have you done investigation SACs yet?
No, our SAC is next term.
Okay, fair enough. Not even in year 11?
We did a little activity, but it wasn't too big.
Okay. So I've noticed from the previous year 12s that the investigation SACs pretty much just ask these kinds of questions, like what happens if d gets bigger? What happens to the graph if d gets bigger? And then you just sort of answer that. They might not say that outright. They might say, here's a full logarithm. What happens as the terms change? Describe some of the impacts. And it might be in the context of a particular scenario that you might then describe those. But fundamentally, it's just stretching. And so you might just reword that in whatever the application question is all about. Okay, so that's that. Reflections work the same way as they've always worked. Only difference is now we have different bases to consider. So if your base was greater than 1, you normally have the green line. And so if you were to reflect that in the x, so with a negative out the front, then it's going to flip that way in the blue. If your base was between 0 and 1, then you already have that reflection. And so putting an additional reflection on that would therefore flip it back to right way up. Bit weird, but easy enough to see the differences there.
Yeah.
Nice. Reflection in the y has the same sort of issues. If your base is greater than 1, then you have green. If your base is between 0 and 1, you have this green. And so all you're doing is reflecting whatever that was to the other side. A negative on the x means you're reflecting in the y. A negative on the x means you're reflecting in the y. Okay, and translations. The only one that really makes a difference for sketching by hand is going to be your horizontal translation, because that'll set your asymptote. So here you've got log 2 of x, which is the green. You don't really draw that asymptote because the asymptote is the y-axis. But in this case, when you have your x minus 2, you're shifting right by 2. And so that's going to set your asymptote. You would have to then draw that. Okay, that's that. If h is negative, so if you have x plus 2 instead, then obviously you're going to be shifting left, just like you would for any other function. Plus means left, and minus means right, as far as the horizontal goes. The reason why this is considered h as negative is because if you have x minus h, then having a negative h means you now have x minus h. That becomes a plus. So that's why I specify that. And I think I mentioned that in the last video as well, or the last class as well for exponentials. Clear enough?
Yeah.
Nice. Okay, vertical translations. These basically don't matter at all. What they end up doing is shifting your graph vertically, but as far as how you would sketch them, you're still drawing the same curve. The only major difference is what you have as your x-intercept and potentially your y as well, if it does have a y. So plus means up, minus means down. That's pretty much all there is to that. So those are all the basics of how logarithms look. Should I clarify anything about that?
No.
Easy. Okay, so how do we sketch these by hand? Well, the only key things that we're looking for here are our vertical asymptotes, our vertical asymptote, singular, our intercepts, which you may only have one intercept, and if at all required, the endpoints based on having a different domain. As I mentioned, vertical asymptote is always your horizontal translation. Only thing I'll clarify, I think you understand this, but I think other people watching might not, is the h term is the term after you've factorized things off of it. So if you have natural log of 2x plus 2, this is not a shift left of 2. This is in fact, after having factorized it, a shift left by 1. So you need to factorize whatever's going off of that. So when you have your x plus 2 over 2, for example, let's say it's just 2x. No, that's fine actually. When you have that, then this technically is already factorized. It just looks like it's all over the same thing. But fundamentally, it's the same thing as if you had said a half out the front of x plus 2. So that's the differences, basically. If you have a coefficient directly on the x as a multiplication, just make sure you take that off of everything in there as a common factor, and then that reveals your true horizontal translation. I guess to explain why that's necessary, the h term being the horizontal translation is kind of just a product of just how logarithms work. So if you recall about the asymptote of a logarithm, we basically can't have a logarithm to have brackets equal 0 or negative. And so if you think about all the terms involved, let's say it's x minus h over d in your logarithm brackets, we're not allowed to have this ever equal 0. And so if we figure out where it equals 0, x minus h over d equals 0, well, you would multiply both sides by d and add h to both sides. So that will give you x minus h equals d, equals 0, just multiply, and then x equals h. And so the d doesn't end up mattering. All that matters is whatever this is becomes your asymptote, the thing that you can never reach. Clear enough?
Yeah.
Nice. Okay, next up, so for the intercepts, so you will always have an x-intercept, unless you have like a restricted domain, for example. Fundamentally, you're just setting y equals 0, like you would for any other function, and then just rearranging. In the context of logarithms, rearranging for x would mean to convert to an equivalent exponential, unless your logarithm was super easy. But fundamentally, you'll always be converting to exponential in any reasonable circumstance. And then y-intercepts may or may not exist. So if we look at pretty much most of these logarithms, like log 2 of x, it has an asymptote on the y-axis. It's not going to have a y-intercept. But for these, they're not going to touch. And so a good way to go around, a good way to save some time is to have a look at the shape of your logarithm based on the terms that are, so like having a look at this, for example, have a look at the shape of what that would look like, and then only then choose to solve your x and y intercepts depending on if they have an x-intercept, or a y-intercept or not. But if you're having trouble imagining what that shape might look like and you do try to find a y-intercept anyway, the thing to watch out for, as I kind of mentioned before, is as soon as you have a negative inside of your logarithm, we're going to stop our solution from then on. That would have a complex number solution or an imaginary solution, not a real solution that's going to exist on our xy axes. And so as soon as you have that negative in the logarithm, you know for certain that this is not going to have a y-intercept. Fair enough?
Yeah.
Okay. So I've got a 6-step process as to pretty much all the key things you have to hit for drawing any, at least drawing any logarithm. First step is always trying to get that general form. That's what I was mentioning earlier by taking coefficients off of the x and, at least in this case, distributing a multiplication through. Finding your asymptote is usually pretty easy from that point onwards. It's just whatever h is. This is what I was talking about earlier by identifying the shape of your graph through the reflection terms. Intercepts may or may not have a y. Endpoint if you have a restricted domain, and then at that point you've got everything you need, and so you can just sketch the curve. So let's have a look at an example. So I mentioned this one earlier. First step is going to be to get our general form, which just means making sure that we can very clearly see all the transformations that are applied to it. So for this one, we're going to bring the -3 through everything first to make sure that we can clearly see what our vertical translation is and what our dilations and reflections would look like. That's going to bring us here. From there, all we're going to do is take that common factor of 2 out the front of the x and the +10, so that will reveal the true horizontal translation. Cool so far?
Yeah.
Nice. From here, we can very quickly see where our horizontal translation is going to give us our asymptote. We have a +5, so we're shifting left by 5, and sure enough, we have an asymptote at x equals -5. From there, we can look at our reflection terms. Technically, you should also look at the base. You could kind of imagine that as a reflection term, depending on if it's between 0 and 1. In this case, we have the natural logarithm, though, and that is a positive base. Natural logarithm has a base of e, and e is approximately 2.7. But we do have a reflection here, and so it's going to cause our graph to dip to the right and down, as opposed to ascend to the right. Now, one of the challenges you have with this when you're doing it by hand is that there's kind of 2 ways you might end up drawing this. And I mentioned this in the exponentials one as well. So if you know that your logarithm is going down and right, depending on how aggressive you draw the curve, so if we go to the handwritten bit now, we know we have asymptote at x equals -5. If you draw it really sharp, you might have that. If you draw it really slow, you might have that. One of them has 2 negatives, the other has 2 positives for their intercepts. And so really all you're doing in this stage is identifying that it goes down and right, rather than if it's going through the positive or if it's going through the negative spots. Clear enough on why that might be an issue?
Yeah.
Yep. So as long as you're identifying that it just goes down and right, that's all we're doing in that step. We can clarify if it's positive or negative when we start solving for our intercepts. Specifically, we can only really look at the x because you may or may not have a y. In this case, we clearly do, though. Okay, so x-intercept, that's right, x-intercept, you're going to set y equals 0, and just rearrange here. So nothing too special, at least at the beginning, you're just getting everything to the same side so the logarithm is on its own, and then just flipping the terms around to convert to exponential. That's going to give you an exact value of this exponential term here, and really all you're looking for there is to figure out, is what I have positive or negative? And so this is where knowing that e is approximately 2.7 is kind of helpful, because you want to know, if I were to raise it to some power, what would it likely be? And in this case, 2.7 to the power of a third is just saying the third root of that number, so already quite small, and then we're halving it again. So really, really small number, subtracting a relatively big number, the net result is going to be negative. Even if you don't know it's negative 4.3, you can pretty confidently say that it's going to be negative. Is the reasoning behind that clear enough?
Yeah.
Okay. So now that we know the x is negative, we can go back to our handwritten bit and say, well, okay, the sharp curve is clearly not going to be correct, and so the only other alternative is the slower curve. And so at that point, you don't even have to care if you don't have to analyze your y-intercept. You already know it has to be negative. So it's a bit nice like that. But okay, we have that. We clearly have a y-intercept, and so we can bother to find it by setting out x equals 0. So you can see trying to analyze the y value here would be a lot harder than trying to analyze the x value. Like having a natural log of 10 in there plus 1, I mean, you could do it by converting to an equivalent exponential, but it's, not pleasant. Much easier just to look at the x. Yeah, so that's our exact value. Exact value. There was no restriction, so we're not going to bother with endpoints. And then we just sketch. So putting all those key features down, and perhaps labeling the curve if you have perhaps other curves to worry about. Fair enough, that one?
Yeah.
Nice. These further notes here were just about identifying whether or not you had a positive or negative x-intercept. So we've already covered what that is, but that's just there as a written form for you or whoever's watching can read up on that. And if we had a restricted domain, all we would do is sub in those endpoints and then solve for the corresponding y values, just being mindful of the brackets. Square brackets means a full circle, and rounded brackets here would mean an open circle. Yeah, and this is just the math of getting the y values. So again, you're allowed to have those as full logarithm answers. A lot of the times you won't have an exact value. Yeah, that's about it really. So that's how we sketch. And those are all his little summary of how each of the terms impact the graph, basically. Anything I should clarify in that?
Maybe can we go through an example of the part where there's a logarithm as the index?
A logarithm as the index, yeah. So one of the solving exponential, one of the solving, yeah, it'd be solving exponentials in that case. Okay, let's see. Can I find an example of that? Probably going to be a 5G. 5G sounds about right for that. Let's see if we can find it. Mm, uh, where's an example of where that would... Oh, it's like 5H might have it. I can see it right there. A log ax equals x. Maybe, maybe not. Most of the time you just replace it with a y though, so I don't imagine it mattering. So a good example. Maybe I'll dig around in the answers and see if I can find one that has that required as part of the solution, and then I'll let you know if we spot one. But while I look
Okay.
in the answers, maybe start back to front on these questions. Maybe even question 9 might do it. I know you have to change the base at the very least, but you may or may not need to do the do that one that you're mentioning where you've got logarithm in the exponent. So we'll start with 9, and while you do that, I'll see if I can find an example of that.
Thank you.
No worries. Not seeing anything in the book, so it's definitely a niche little thing. Sure, it's some exam question. I'll have a look in there as well.
I think for question 9, we
Mhm.
do have to use that.
Oh, okay. The answers don't use that specifically, but I could imagine the log laws can apply in all sorts of scenarios. So if you do find an answer with that, I wouldn't be surprised. Yeah.
Yeah.
How's that going so far?
I got the I did it in a way where I now have a log as my power.
Yep. Okay. So I guess have a keep going with that and see if you can find a solution with that. And
Yeah.
if not, just sing out and we can see where to take it from there.
Okay. Thank you.
No worries.
I am a little bit stuck on that question. I
Mhm.
have no clue where to go from where I am.
Sure. Okay. So let me know where you're at, and then we can take it from there. What do you have written down?
I've so I changed it into the log being the power, and then I made that equal to y, but I don't know where to go from there to solve it.
Log being the power. So you're doing question 9, yeah?
Yeah.
Okay. So you're starting at log 5x and you're equaling 16 log x5. And so what does the next step from here look like?
Um, I changed it to 5 to the power of 16 log x5 is equal to x.
16 log x5 equal to x. Yes, that's not quite the same thing because what you want to have is same base in the power and in the base of your, sorry, in the base of the logarithm and the base of the exponential. In this case, you have 5 over here and x over there, so it doesn't quite work out using that identity. I wonder, so this one, you would have went, this is the current base. if you do it the other way around, dividing that by 16, you'd have x to the power of... Yeah, okay, so either way you do it, you're still going to have different bases, unfortunately, so that identity doesn't quite hold for that. So makes sense why you're having a bit of a difficulty getting there. What else could you possibly do instead of converting? Because you're trying to solve for x. What's the way you can imagine to free the x?
Put the 16 onto the other side.
Yeah, okay. So we can say 1 over 16 log 5x is equal to log x 5. So I guess one of the challenges we have here is that x is in both the base and the bracket here. So it's a bit
Yeah.
difficult to imagine how you might go about things. There was a technique that I mentioned that would allow you to free something from the base of a logarithm.
Multiply both sides by the base you need. Is it that one?
Yeah, so you wrap both sides with the base, but only after you convert it to exponential. So if we have a look at what that was, converting the base of logarithm, you start by converting your logarithm to an exponential, then you wrap the logarithm around that and rearrange afterwards. So if you were just to try and wrap logs around logs, that would be kind of complicated. Not to say it's not doable, but it makes it more complicated rather than less, unfortunately. And so one thing you might want to do is, if you're looking to free the x from this base, then you might just look specifically at this logarithm and say, hey, I'm just going to take this specifically and then try to convert this to a new logarithm. So you can either do that with those 3 steps, or you can do that directly with that equation. You said you preferred the 3 steps, rather. And so one thing you might want to do is say, well, okay, I've got this logarithm, I want to convert it. First things first, let's pretend it equals some value y. It's from here that you would then convert this to an equivalent exponential form. So you'd have x to the power of y equals 5. Cool so far?
Yeah.
Now if you apply a logarithm to both of these sides, then you can start getting it to where you need it to be. So you can technically pick any base that you want. What base do you think would be most appropriate on this side of things?
X.
Okay. So we have log x of x, x to the y rather, and we have log x of 5. That's wrapping both sides. So if we then want to get back to y, which is what this thing originally was, what might you do?
Take the y on to the outside of the log.
Yep. So you have y equal, well, y at the front of log x of x. Anytime the
Yeah.
base and bracket are the same, they cancel, and you just get back to y equals log x of 5, which unfortunately is where we started. So maybe not picking a base of x. What else is another possible base we could choose?
Y.
Choosing a base of y would add a lot of y's to it. We're trying to rearrange to get y on its own afterwards, so that will be a bit difficult. The base that I have in mind is a base of 5. So the reason why a base of 5 will be appropriate is because when you take the log of both sides, that right-hand side will cancel down. So if you have log 5 x to the y equals log 5, 5, well, log 5, 5 is just 1. And so that's going to disappear. You put the y at the front, you have y equals, sorry, not y equals, but y times log 5x is equal to 1. And then to get the y on its own, finally you have y equals 1 over log 5x. So what we have achieved is we started out with y is equal to this logarithm. Now we know an equivalent logarithm is this. The major difference is that instead of the x being inside the base, it's now inside the bracket. Okay?
Yeah.
So from here, what we've said is we have this initial equation. So instead of saying log x of 5, another alternative is to now say 1 over 16 log 5x is the same as 1 over log 5x. And so we can just put that in there. 1 over 16 log 5x is equal to 1 over log 5x. Do you want to take that from there on your own, or continue working through this together?
Can we continue together?
Yep, yeah, absolutely. So what might we do as our next step? I'll still make you think a bit.
Get rid of the fractions by timesing log 5 of x.
Yep, log 5x to both sides. So it's going to give you 1 over 16, and, well, log 5x times log 5x is just the same as log 5 of x all squared. That's going to equal 1. What else might you do?
Times the 16 to the other side.
Yep, so you're going to have log 5x all squared is equal to 16. That's good.
The square root of
Square root.
both sides.
Yep. Log 5x is equal to root 16, which is what?
Plus or minus 4.
That's good. Yeah, never forgetting the plus minus. That's good. And so now that you have the plus minus 4, what might you do?
Put it in an exponent. So 5 to the power of plus or minus 4 is equal to x.
Nice. Yeah, exactly. And that is perfectly mathematically suitable. For anyone watching the video who might not be comfortable with doing that, what you could do is just split it up into two individual equations. You might do log 5x equals positive 4, log 5x equals negative 4, and then put each of those into their own exponentials by flipping. But this is perfectly fine as well. In fact, it's a more succinct answer, which is good. So yeah, that one intended, the intended solution there was to use the converting base to solve that. Although, what could you do? Well, I mean, now that we're kind of talking about it, if we did get up here, or you had 5 to the power of 16 log x5, you could take this 16 log x5 and convert it to a new base of 5, and then technically you could use the rule that we had a look at there, using the exact same feature that we just sort of talked about then. So all that goes to say is that you can solve things in a lot of different ways. Can you see how you might be able to use that fifth identity by converting the base of this logarithm?
Yeah.
Yeah. So that might be another one just for funsies if you want to do that in your own time after the call. We've only got 5 minutes or so, so I guess if there's anything else I should clarify.
If we did it that way, would we end up with a fraction?
Yeah, might as well. Let's see if I can blitz through that. So we're going to have 5 to the 16 log x5 is equal to x. Now we can sort of use our previous working out to simplify that. So if we know that log x of 5 is the same as 1 over log 5x, then we're just going to replace this with 1 over log 5x. Oh, is this going to work? Huh. Because you are going to have a fraction, yeah. So you're going to have 5 equals 16 over log 5x is equal to x. I wonder. No.
Would we be able to just say then that can't we leave it like that maybe? Because we technically already found what x is.
Well, the issue is that we've got an x in the brackets as well.
Oh.
That's the only main concern there. I was thinking maybe you could do something like 5 to the 16 log 5x to the power of -1. But I don't. Can you put this through? Maybe you can. Because you can put things through roots if you square it on the way in. So presumably you could put things through a power of -1 if you invert it on the way in. Does that make any sense? So if I have a to the -1 times 16, is it the same thing as saying a over 16 all to the -1? Yes, it is. Because the -1 distributes to both.
Yeah.
Okay, that works then. So what we could do from there, perhaps, would be to say 16 to the -1, I guess just all of it. You'd say 5 to the 16 log 5x all to the -1. Put this as a power, but you still got this -1, that's the issue. A logarithm raised to a power doesn't have a log law. It's only if the brackets are a power. You can do it anyway. So log 5 of x to the 16, so -1 equals x. Now it's a -1. What do? Yeah, I think this power might throw things out of whack. Because if you just use that identity, then we're basically just saying that x to the 16 equals x. So you've got to do something with this, because that's clearly not it. What might you do? Is there something to be done?
Would you flip both sides? Or would that not work?
Flip both sides. Raise both sides to the power of -1. What's the index law associated with that? So if you would have a to the b equals c, and you raise both to the power of -1, that would do a to the b to the -1 equals c to the -1.
So it
And
would
then,
be 1 over a to the power of b and 1 over c.
yeah, but b will still be whatever this whole thing was.
Yeah.
Because when you have cascaded powers, they multiply, they don't cancel. So, hang on. Well, that means that might be a good thing then. Hang on. Yeah, so what if we. Okay, yeah, that's a very good idea. So 5 to the power of log 5 x to the 16 is equal to x to the -1. Because if you raise both to the power of -1, -1 times -1 gives you the cancel out. Well, that's still bad. So we've done something mathematically wrong there.
I think maybe if we're making.
Oh,
Never
the
mind.
16. Oh, the 16. Because that should. No, it's inside there. I was thinking maybe over here, but no. Yeah, I don't know. Something to ponder. Point being, we've overcomplicated it, so maybe we shouldn't be doing
Yeah.
it this way, but I feel like there's something there to do. There's probably something, and I'm just not seeing it right away. But yeah, takeaway message is where possible, use a conversion of base rather than having to go through and use this identity. This will make itself known through your working out just sort of naturally. I've found that's pretty much been always the case when this has come into play. It kind of naturally occurs rather than trying to force it. So yeah, see if you can have a mess around with the functions and relations practice act that I've got in my in the classroom? Because I've seen this come up a couple of times. If it's not the Cambridge book, it could be the Jacaranda book, and if it's not that, then surely it's got to be in the Sachs. I don't know where else I would have seen it.
Yeah.
But yeah, that's pretty much all I've got then. So that's time for the class. I appreciate you coming. If you have any questions, of course, feel free to DM me or make a post in school. Any of that is acceptable.
Thank you.
No worries. Have a good day,
Have a
Elise.
good day.
Thank you.